Good day, students. The fourth lesson in Module 5 is about valence band theory and hybridization. So what is valence band theory? Before that, how does Lewis' theory explain bonding in hydrogen and fluorine? Remember, according to, or in Lewis structure, diba, hydrogen, or in forming a hydrogen molecule, we have sharing of electrons. No? So there is sharing of electrons between the two atoms. Same with the fluorine molecule. A bond is formed by sharing of electrons. So that is what we have learned from Lewis theory. No? Bond is formed by sharing of electrons. However, in experiment, the bonds in hydrogen and fluorine have actually different lengths. No? For hydrogen, it's only 74 picometers, while in fluorine, it's longer. It's 142 picometers. And the two bonds have also different bond enthalpy. This is the energy that is required to remove, or to break that bond. No? So Lewis theory cannot explain these data. So now we have our valence band theory to answer these concern. No, when we say valence band theory, according to valence band theory, electrons occupy orbitals, no, and bonds are formed by sharing of electrons from overlapping atomic orbitals. So this explains why we have different bond enthalpies and bond lengths for hydrogen and fluorine molecule, because according to valence band theory, it's actually the 1s orbital which are overlapping to form the bond, while in fluorine we have 2p orbitals which are overlapping to form the bond. No? So the answer to this data is that hydrogen and fluorine have different orbitals used, no, in forming the bond. That is why they have different bond lengths and bond enthalpies. So here we have example. We have for hydrogen molecule. No? So we have two hydrogen atoms. We have our first hydrogen atom and our second hydrogen atom. So as the two atoms are still far apart, no? Remember that in an atom we have our nucleus in the center, and this is positively charged because of the presence of protons surrounding the proton lang for hydrogen. Surrounding this nucleus is electron. No? So as the two hydrogen atoms approach each other, what happens is that there could be two interactions. No? There could be attraction, because we have our electron here from one atom and we have our nucleus in the other atom. So this electron could be attracted to the nucleus of the second atom because they have opposite charges, and opposite charges attract. And same with the other atom. So we have our electron, of course, from this atom, and it could also be attracted to the nucleus of this hydrogen atom. So that's first, there could be attraction from the electron to the nucleus of the other atom, and there could also be repulsion, because electrons here, or the electron here in one of the hydrogen atom, could be repelled by the electron of the other atom, because again, like charges repel. Also, there could be also repulsion from the nucleus of this atom to the nucleus of the other atom. However, no, as they are still approaching, of course, the distance is not that close, so the stronger interaction is the attraction of the electron towards the nucleus of the other hydrogen atom. So what happens then is we have the energy are slower, no, because of this attraction. By the way, before they come closer, our energy here is zero because there is no interaction, there is no attraction, there is no repulsion. Now, as the two atoms come close, attraction from electron of one atom to the nucleus of the other atom prevails over the repulsion. No? So as the two atoms move closer, they would um, arrive at one point when there is optimum distance between the two, and so we have our minimum energy. So that is when the hydrogen molecule is now stable, no? The optimum distance between the two atoms. Now, if the two atoms move closer again, what will happen now is that the repulsion will prevail, no? Because the distance is too close, so electrons will repel each other as well as the protons in the nucleus. So now what will happen is there is increase in energy because of the repulsion. So here is where our minimum energy is and where our stable hydrogen molecule is formed. Here is another picture of the as two hydrogen atoms approach each other. We have our electron cloud, by the way. So the red here are our electrons. So as they approach each other, the electron feel the nucleus of the other atom. So it is now attracted to the nucleus of the other atom. And then we have here now start the electron density between the two atoms until such time that we have now our optimum distance between the two atoms and the stable hydrogen molecule is formed. So now we have the overlap of the s orbitals of hydrogen atoms, and now we have our bond formed. Okay. Valence bond theory and ammonia. So how does valence bond theory explain the formation of bonds in ammonia or in NH3? Okay, recall that the electron configuration of nitrogen is 1s2, 2s2, 2p3. So when we put the electrons in the orbital, this is our 1s. So we have our 2 electrons. This is our 2s. We have our 2 electrons. And these are our 2p orbitals. We have our px, py, pz. So we have 1 electron for each orbital. Hydrogen, on the other hand, has electron configuration of 1s1. So in bonding, for example, the electron from the hydrogen could pair with the empty or the singly filled p orbitals of nitrogen. So this one here is from our first hydrogen atom, and this is the 1s electron of the second hydrogen atom and the 1s electron of the third hydrogen atom. Now, if the bonds form from overlap of the p orbital, this is the electron of the p orbital, so this is the p orbital, and this is the electron of the s orbital of hydrogen. So if bonds form from overlap of the 3 2p orbitals of nitrogen with the 1s orbital on the hydrogen atom, what would the molecular geometry of ammonia be? Remember that we have again 3 degenerate p orbitals. We have px, py, and pz. If the p orbital is px, the orbital is along the x-axis. For py, we have the orbital along the y-axis, and for pz we have the orbital along z-axis. So if this is true, if it's the 2p orbitals overlapping with the 1s orbital of hydrogen atom, our bond angle should have been 90 degrees. However, in reality, the H and H bond angle in ammonia is actually 107.3 degrees. So how should we explain this? Now we have the so-called hybridization. This is the mixing of 2 or more atomic orbitals to form a new set of hybrid orbitals. So what is the process of hybridization? Here there is mixing of at least two non-equivalent atomic orbitals. Like for example, S is mixed with P. No? Hybrid orbitals have very different shape from original atomic orbitals. We know that S is spherical, P is dumbbell. So when S orbital is mixed with P orbital, the hybrid orbital form is not spherical and not dumbbell. It has different shape than the original atomic orbitals. The number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process. Like for example, if one S is mixed with P, so if you have one S and one P mixed, the number of hybrid orbitals formed would be 2sp because of 1 and 1p. If we mix 1s and 2p, for example, the number of hybrid orbitals formed would be 3. 1 plus 2 is 3. So we have 3 s p 2 because we have 1s and 2p. So the 2 here becomes the superscript of p. So covalent bonds are formed either by overlap of hybrid orbitals with atomic orbitals or the overlap of hybrid orbitals with another hybrid orbital. Okay, first we have the formation of sp3 hybrid orbitals. How is this formed? By mixing 1s and 3p orbitals. So that's why it is called sp3 because we have 1s and 3p orbitals. So how many sp3 hybrid orbitals are formed? We have 1 plus 3, we have 4 sp3 hybrid orbitals formed. And as I've mentioned earlier, the hybrid orbitals have this different shape than the original atomic orbitals. So if this is spherical and the p orbitals are dumbbell, our sp3 hybrid orbitals are neither spherical nor dumbbell. No? So these are the shape of our sp3 hybrid orbitals, and they are directed to the corners of a regular tetrahedron. So we have our corner here, another one here, here, and here. Okay, so hybridization is the answer as to why the bond angle of ammonia is 107 and not 90 degrees. No? So what happens in ammonia is that, remember, what is the configuration of ammonia? We have, nitrogen, we have 1s2, 2s2, 2p3. So here we have our 2 electrons for 1s2, and then we have 2 electrons for 2s and our 3 electrons in the p. So we have our 1s, 2s, and 2p. So what happens here is that the s orbital here overlaps with the 3p orbitals to form 4 sp3 hybrid orbitals. Okay, so these blue here are our 4 sp3 hybrid orbitals, and they're the ones used or overlapped with the s orbital of the hydrogen atoms. Okay, so that is why we have 107 degree bond angle. Another example of sp3 hybridization is, using sp3 hybrid orbitals in bonding is in methane or CH4. The electron configuration of carbon is 1s2, 2s2, this is for carbon, 2s2, and 2p2. So when we put the electrons here, we have for 1s, we have our 2 electrons. Then for 2s, we have our 2 electrons. And for 2p, we also have our 2 electrons, singly first. Okay, so what happens in carbon is that one of the electron in the 2s gets promoted or gets excited. So to do this, So one of the electron gets excited and promoted to the p orbital, no? So we have our vacant p orbital here. One of the electron in the 2s now gets excited or transferred to the one of the p orbitals. So now here, after that, after it gets promoted or gets excited to a higher orbital, the s orbital now will mix or hybridize with the three 2p orbitals to form again 4sp3 hybrid orbitals. And these hybrid orbitals are the ones in blue lobes, okay? And they're the ones used to overlap with the s orbital of hydrogen to form the bonds or the covalent bonds. Next, we have formation of sp2 hybrid orbitals. So we say sp2, that means we have one s and two p orbitals mixed. So how many sp2 hybrid orbitals do we form? We have 1 plus 2. We have 3 sp2 hybrid orbitals formed. And each of these are directed to the three corners of a triangle. So, example, we have in boron trifluoride. That's the configuration for boron. Well, for boron, we have 1s2, 2s2, 2p1. So we have, there are 2 electrons in 1s, 2 electrons in 2s, and 1 electron in p. Same with carbon. One of the electron in 2s gets promoted, gets excited. So it goes to one of the vacant p orbital in boron. So now we have 1 electron in the 2s and 2 electrons in the 2p. After that, after it gets excited, one of the s orbital here mixes with the 2p orbitals, which has 1 electron each, to form sp2 hybrid orbitals. And these sp2 hybrid orbitals are the ones which overlap with the p orbital of fluorine to form the covalent bonds in boron trifluoride. Next, we have formation of sp hybrid orbitals. So in sp, we have of course 1s and 1 p orbital mixing to form 2 sp hybrid orbitals. Okay, so we have here our 2 sp hybrid orbitals formed. Example is in beryllium fluoride. Beryllium, the configuration for beryllium is 1s2, 2s2. Okay, we don't have a p for beryllium. However, if that's the case, beryllium wouldn't have been able to bond with another atom. So what happens here is that one of the electrons in 2s goes to one of the p orbitals. No? Same with boron and carbon. So now we have 1 electron in 2s and 1 electron in 2p. After that, the s orbital and one of the p orbital now mixes to form the 2 sp orbitals, hybrid orbitals. And these are the 2 hybrid orbitals. We have 1 and 2. So one of the hybrid orbitals is used to overlap with the p orbital of the chlorine atom to form that covalent bond, and one with the other chlorine atom. So we have 2 bonds here. We have our beryllium chloride. Okay, so this bond is from the overlap of these 2, and this one is from the overlap of these 2. So here we have VSEPR and hybridization. So if you know the class in VSEPR, geometry, you'll also know the hybridization of that molecule. Like for example, if the molecule has class AB2, that's linear, it's geometry, its hybridization is SP. If the molecule has class AB3, for example, its hybridization is sp3. Okay, so you have to familiarize this, no? So that you will know, you can tell right away the hybridization of the molecule. If the molecule has AB2E class, its hybridization is sp2. For AB5 down to AB4E2, hybridization, we have d orbital involved. Okay, for AB5, AB4A down to AB4A2. But for our assessments and for exams, we will only um, use the uh, hybridization for, using S and P orbitals, okay, for simplicity. So we will not use molecules which um, involve the orbitals in hybridization, only the S and P orbitals.